You know when you throw a ball and you watch it sail through the air, it seems to follow one single predictable path, right? Well, what if I told you that's all an illusion? Okay, let's really get into this, because what's really going on is so much stranger and, frankly, so much more beautiful than you could ever imagine.
So yeah, this is the core idea we're going to tear apart today. Our everyday world, the solid reality we touch and see, is built on this foundation of quantum weirdness. A world where single paths just don't exist. Instead, to get from here to there, an object takes literally every possible route you can think of, all at the same time.
To wrap our heads around this, let's start with a classic example. Imagine you're a lifeguard on a beach, and you see someone in trouble out in the water. What's the fastest way to get to them? Well, you're not going to just run in a straight line, because you run way faster than you swim. But you're also not going to run all the way down the beach just to make the swim shorter. You'd instinctively find that perfect angle, that sweet spot in between, the path that takes the least amount of time. Now here's where it gets really interesting. Light does the exact same thing. You know when you see a straw in a glass of water and it looks bent? That's light taking the path of least time. But hold on a second. A lifeguard has eyes and a brain. They can see the whole situation and figure it out. How on earth does a beam of light know the fastest route before it even gets there? The answer to that question was about to break physics. To find that answer, we actually have to jump in a time machine and go back to the turn of the 20th century. This was a time when a problem that seemed really simple, just understanding the light coming off a hot object, led to a total and complete breakdown of everything we thought we knew. So believe it or not, this all started with people trying to invent better light bulbs. They were measuring the light from a perfect glowing object, what they called a blackbody, and they saw this nice predictable curve. But when they tried to predict that curve using the classical physics of the day, the theory just went completely haywire. It predicted that these objects should be blasting out infinite energy. I mean, obviously that's wrong. This failure was so massive they called it the ultraviolet catastrophe. Physics had officially hit a brick wall.
All right, so enter our hero, Max Planck. His professor had actually told him not to bother going into physics because pretty much everything important had already been discovered. Yeah, good thing he didn't listen. After years of failing to solve this problem, he was ready to try something completely radical, something he himself called an act of desperation. Planck basically said, okay, what if energy isn't a smooth, continuous flow, like water from a tap? What if it's lumpy? What if it only comes in these tiny individual packets, which he called quanta? And the killer insight was this. The energy of each packet, E, was tied to its light frequency, F, by a new number he basically just invented, H. And with that one change, boom, the problem was solved. High-frequency light would need a huge energy packet, which was super rare, and that perfectly explained why the curve dropped back down to zero.
The formula was absolutely flawless. It matched the real-world data perfectly. But Planck himself kind of hated it. He thought it was just a clever mathematical trick. He had discovered this new fundamental constant of nature, this H, but he had no idea what it physically meant. It was like he'd found a key to the universe, but he had no clue what door it was meant to open. It turns out the answer was hiding in this old, kind of weird concept in physics called action. Now, it's a bit abstract, but you can basically think of it as a number that measures the total effort of a journey. It's a combo of the energy used and the time spent using it. Physicists had known for a while that things in nature always seemed kind of lazy. They always pick the path that minimizes this action. But most people just thought it was a neat mathematical coincidence. And this is the moment everything changes. After weeks of hard work, Planck realized that his constant H had the exact units of action. It wasn't a packet of energy, it was the smallest possible packet of action that could ever exist. This lazy principle wasn't just a curiosity anymore. It was the fundamental, grainy texture of reality itself.
So this idea that action is quantized, that it comes in little chunks, is what kicked off the whole quantum revolution. And decades later, a physicist named Richard Feynman would take this concept and run with it to a conclusion so bizarre it just rewrites everything we know.
And you can just see the dominoes start to fall. After Planck, you get Einstein saying light itself comes in packets called photons. Then Bohr uses quantized action to finally explain how atoms work, and then de Broglie comes along and says, you know what? Maybe everything has a wavelength. Electrons, baseballs, you, me. The stage was set for something huge. Now, there's this great story, maybe it's true, maybe not, about Feynman as a student. He's sitting in a lecture about the famous double-slit experiment.
The one where a single particle seems to pass through two slits at once. And while everyone else is just trying to take notes, Feynman's mind starts to wander.
He starts thinking, okay, so it goes through two slits. What if we add a third slit? The math works, you just add another possible path. Okay, what about a fourth slit, a 10th, a million? What if you just keep adding more and more slits until the wall isn't even there anymore?
Do you see where he's going with this? The logic is totally inescapable. If you accept what happens in the double slit experiment, then you have to accept that even in totally empty space, a particle explores every single possible path to get where it's going. Not just the straight one. I mean the paths that loop around the moon and back, the paths that zigzag. The math demands that you have to account for all of them.
So of course, this leads to the big question. If a beast ball is really exploring every path through the universe, why on earth do we only ever see it follow one single clean arc? Well, the answer is this absolutely beautiful phenomenon called interference.
Okay, so for every one of those infinite paths, Feynman imagined a little spinning arrow, like the hand on a stopwatch. The final direction that arrow is pointing when the particle finishes its journey is called its phase. And, this is the critical part, how fast that arrow spins is determined by the action of that specific path.
Now, for all the really crazy looping paths, their action values are going to be wildly different. So their little stopwatch arrows end up pointing in all sorts of random directions. You add them all together, one points up, one points down, another left, another right, and they completely cancel each other out. Poof! They vanish. This is called destructive interference. But something really special happens for all the paths that are really close to that least action path we talked about. Because their actions are all so similar, their little stopwatch arrows all end up pointing in almost the exact same direction. So when you add them up, they don't cancel, they reinforce each other. They build up and create one giant, super strong arrow. And that's constructive interference.
And that's it. That's the solution. The single path we see in our everyday world isn't the only path the object takes. It's the overwhelming average of all the infinite paths that just happen to agree with each other, while all the other bizarre paths just cancel themselves into oblivion.
Now, this isn't just some clever way to think about things. This is arguably the most fundamental principle in all of physics. And what's even cooler is that we have experiments that prove this is really happening.
Okay, check out this experiment. It's incredible. Someone shines a light at a mirror, but they block the exact spot where you'd expect the reflection to appear. Then, they take a special grooved plate and put it on a totally wrong part of the mirror, a part that should be doing nothing. This special plate is designed to undo the cancellation effect, and when they do that, a reflection appears. An impossible reflection, coming from the wrong spot. It's definitive proof that the light was taking that path all along. We just couldn't see it before. So, to bring it all home, this isn't just about quantum weirdness. This principle is why balls follow parabolas. It's how planets orbit the sun. The principle of least action is the foundation of classical mechanics, of Einstein's relativity, of electromagnetism. It's basically the underlying rulebook for how the entire universe operates.
And that leaves us with this one last profound thought. When you hear physicists talk about searching for a theory of everything, what they're really looking for is one single thing, a master equation that defines the action for our entire universe. If they can find that, they found the source code for reality itself.